Shantanu, thank you for the introduction. My student Zhilu did most of the work. She was very excited about the conference. Unfortunately, her government, which is the Communist Party, forbids her to travel. So I will present this paper. So my group really focuses on electromagnetic antennas and circuits for sensor applications and optical imaging and sensing. So this is the outline of this talk. I think we will first have an introduction about food sensing and what is important. And then we propose a market food sensors to why this is alter the food quality and condition. So we are going to monitor the pH value and also the concentration of ammonia. And we use a packaged food, a milk, as an example, and finally I'll draw a conclusion. We know many developing countries they are suffering from food crisis, and developed countries we wasted lots of food. So it's important to monitor the quality and condition of packaged food before we dispose this food when they are still safe. But when you open the food, open the package, then you can overuse the food. So of course, you need to open it and use probe to understand its condition. So here we propose a wide solution to monitor the quality of a packaged food. And however, if you want to make the sensor very small, in order to not affect the food condition, then the small sensor, if it's also battery-free, maintenance-free, the problem is it's hard to detect to accurately interrogate the sensor because of the clutters, echoes, self-jamming, and the multiplexed scattering. All of them can interfere detect signal. For example, I launch a continuous wave, CW wave to the sensor, and I measure reflective signal. If they are at the same frequency, the problem is you see interference, and then it's hard to detect the resonance. And of course, if you measure the device in the anechoic chamber without any interference, you can get clear resonance response in this radar cross-section. So we want to address this problem, and we propose a new technique called harmonic sensor, which I'm going to introduce next. So yeah, this is an example show you, for example, if I have a tiny sensor, human body for biomedical application, you will see interference because our human body, in this case, is a clutter source. Several years ago, I read a paper about harmonic radar. So also, we are losing the population of bees, which is also important for the crisis. So people try, but the thing is that if you want to monitor RCS, radar cross-section of an insect, its physical size is too small. So the major RCS is almost like a noise. So how we can distinguish RCS from a tiny object? We can launch a fundamental and detect harmonic or intermodulation signal. So because of the frequency, the two frequencies are also then we can clearly track the field. Any object with small RCS. Then I'm thinking about, so for example, this is a tiny sensor, the microchip, and this is a bee. They look similar. So probably we can apply the same concept, harmonic radar. And then when we do some manipulation, we make a harmonic sensor. So the sensor can receive fundamental and backscatter second harmonic. So we can, even the sensor is battery-free, without any digital memory, without any non-volatile memory, without any backscatter, you can still detect the sensor. So this is the knowledge between the harmonic, traditional RFID, the comparative between traditional and harmonic RFID. In harmonic RFID, we launch a fundamental. We launch a fundamental, and this guy can retransmit the second harmonic. So because of these two frequencies, they are orthogonal to each other in the frequency domain. So there's no interference. So even the background median, the clutter, and the ground, and the scatter, they can backscatter the same, so the signal in the same frequency, but we can eliminate this interference, EM interference. So this is a sensor field from a student, and we'll use this to monitor the quality of the meal. So this is the hardware architecture. So basically, we have antenna one, which could receive fundamental And then we have a power divider, the passive power. So before the power divider, we have the frequency multiplier to double the frequency. So this guy receives fundamental tone, double the frequency. And then there's a power divider. And to send a signal to two antennas, antenna 3, antenna 2. And these two antennas are small antenna, high Q antenna. And they are connected to a sensor, a pH sensor and a ammonia sensor. So this is a chemically tuned varactor. So if there's any pH change, it will change the potential across these two electrodes. And if you connect the electrode to a varactor, so this will change the loaded capacitor. So it's a capacitively tuned antenna. Same mechanism can be applied for ammonia sensor. If I have a chemical doping, I change the chemical potential to bias the varactor, and then I change the resonance frequency of this antenna. So these are some hardware design for this sensor. So my students first measure the return loss and the radar, return loss and the radiation pattern of the sensor. So this is for antenna 1 used to receive fundamental tone. This is for antenna 2 and antenna 3. They are used to receive retransmit second harmonic. So and antenna 1 is a relatively wideband antenna, and antenna 2 and 3 they are narrow band high Q antennas. So the design is very simple. If I have impedance transformer to increase the real part of impedance of the antenna. Okay, and so these are some we can find this structure for us microwave engineering textbook. So and this is a proof of concept we didn't optimize. Theoretically, we can push the limits to 96 dB, and this just 3 dB power divider. So then my student done some work with home antenna to interrogate harmonic sensor indoor environment. So here we use a different technique. We use a frequency half spread spectrum, FHS technique, which is comparable to RFID C1 Gen 2 protocol. So for example, we can half the frequency. We send the monotone frequency. We half the frequency. We first send the monotone to the reader, and reader can receive the monotone and transmit the second harmonic. So because the two antennas I showed earlier, these two antennas, they act like a filter. So if you try to send a frequency half monotone to the sensor and detect the second harmonic, so you will see two peaks. This peak represents the resonance frequency of antenna 2 and antenna 3. This guy. So this guy is used to receive the monotone. These two guys, they can transmit the second harmonic. But so if you look at the ISSI pattern, you will see two peaks. So they correspond to the resonance frequency of two transmitting antennas. So for example, this is how we do. So it's okay to do the measurement. So we try to measure the envelope of ISSI pattern, and if there's any change in pH value or the concentration of ammonia, two peaks will be shifted. So this is our measurement result. We can measure the shift in the peak frequency. So we have a wide monitor the food quality. For example, this is a packaged meal. We can monitor pH value change with time. So basically, we monitor the food quality in 5 days. So this is the conclusion. So we propose a compact and fully sensor and low cost multifunctional harmonic sensor for food quality control. And we also apply this technique to other applications like vital sign monitoring, or so here, for example, here we build a smart face mask. And also we are trying to integrate with the microfaraday channel for some medical applications. Okay, so thank you very much.